So let me, oh, and the meeting is being recorded. Awesome. So let's just check first if you can all like type hi, just to check that that people are awake. I realize it's 2 in the afternoon, so we should all be awake. But if you could just type hi, and there you go, there you go. Okay, people are here. That's good. Hello. I am going to share my screen. There you go. Cool. This talk was inspired by a tweet. So I don't know if you've seen this one, but yeah, you might have been in a situation where you're like totally stuck with your code, and that and it's like not fast, it's not documented, and it doesn't even work. And so this series of lectures is actually made to address this kind of problem. I think that Control L is full screen. Oh yeah. So many of you might be doing coding heavy research, but you're not CS people, or you don't know anything about software engineering, or you never trained for it. And what might happen if you're in that situation is like you might feel like you don't quite know what you're doing, and you might have imposter syndrome, or your productivity might be quite low. You have a lot of bugs in your code, and you hate your code, and you don't want to work on it, and then you never graduate or whatever. I wouldn't know anything about that because I graduated in 6.5 years, so it's no problem whatsoever. But anyways, it doesn't have to be all bad. So I have a bit of a weird perspective on this. So I did a PhD in neuro at the MNI, doing computational neuroscience, and then I was broke, so I decided to go to industry, and I became a wildly underqualified software engineer at Google, where I picked up some things. And it was very stressful, but I made it through to the other side. I also worked at Facebook on BCI. And last year did a lot of technical stuff for Neuromatch Academy. So I am here to prevent you from, or like to talk to you about ways to prevent these sorts of issues. Like I said, I've wasted months of my life just making bad code and of my own making. But I wish I knew a few different things. And the thing that I think the thing that I would have liked most to know about is how to do testing. Because I realized that it's very underappreciated and underused in coding for research code. So this is, and sorry, this is a very busy slide. I guess I just generated it and then I didn't look at it, so I apologize. I'm going to assume you know a little bit about Python. I know there was a Git intro and a command line intro as well. If you haven't really caught up on these topics, you can do so by your software carpentries. This is a beginner-friendly sort of thing, so I don't expect you to have any experience in releasing code or distribution or packaging or anything. This is like the kind of workflow that I'm talking about is totally fine if you're basically the only consumer of code. And this is a subset of a longer series of lectures that you can refer to. There's like 5 lectures in there. One day I will record them, but the problem right now is that every time I record it, I hate my face, and it's just been like this problem that the sound of my voice just really annoys me. But I will get to it. I will get to it eventually. And interrupt me in chat. So if you can just write +1 right now in the chat, just to make sure you're still awake. Yes, awesome. Thank you. And these are the learning objectives. We're going to go through what is testing, what should you test, how can you test, and how can you integrate testing into a into a project that you're working on right now. Sam says we can record all the talks this PM if you want. Yes, but I will definitely edit them for just hours and hours and hours. It's really bad. Okay, so building around testing. This is in the README from Ariel Rokem for Shablona, which is like a packaging template. I'm just going to read it. So most scientists like yourself who write software constantly test their code. You try to see how well your code works by running every new function you write. You examine the inputs and the outputs to the function. You make sure that it runs properly without error, and then you test whether the results, they make sense. Automated code testing just takes this informal practice, makes it formal, and automates it so that you can make sure that your code does what it is supposed to, even as you go about making changes around it. I think that's a very good way of putting it. It's to give you some guardrails, as you're moving quickly and hopefully not breaking things. So let's start with kind of an open discussion for you. So let's say that we have a function in fib.py, and this function is this. I'm sure that this will be a familiar function. It's a function that calculates the Fibonacci sequence or the F number in the Fibonacci sequence. It's not a very efficient way of implementing it, but let's roll with it. So what can we test about fib.py, and what does it mean to test in this context? And so to frame the discussion, I'm going to say, like, let's say that you had this function and you wanted to convince yourself that it actually works. What would you check? And I'm going to look for the answers in the messages. Okay, so we have from Abigail, we have if it returns a proper output based on different inputs. Yeah. Patrick says run fib2 as a unit test. Cool. A value less than 2 and a value greater than 2. So those are edge cases, right? So and specifically it's about path coverage, which is something we'll talk about a little bit later. Yeah, those are all good answers. So I think that one thing that we can test about fib is correctness, right? So there's a mathematical definition of what the Fibonacci sequence is. I'm sure many of you remember this, but if you don't, that's totally fine. So the sequence goes like this. And so we have to test that every one of the cases gives the results that we expect. Or rather, like, we can't check like all the infinite results, but it would be nice to check it. Another thing that is very common to test is edge cases. So if you test it with the value 0, for instance, that's an edge case because it's like on the edges of it's like on the edges of the good inputs, if you want. And so it's good to test that it does the right thing. And if we try to call the function with bad input, it should output us an error. So that's kind of like a broad overview of the kinds of things that we can test. There's other kinds of tests that we can run as well. But when we have this kind of a computational code, if we just assure ourselves that it gives the right results on a couple of test inputs and it has like a good coverage, then we're in good business. So let's see what we can do here. Let's go ahead and maybe write. I realized that I have this PDF open. So this is from scratch, and we'll write a third one from scratch because I've written this code a bunch of different times already. So let's call this fibbed and fibbin test. And so I'm just going to try to remember off the top of my head what fib does. So if n is greater than 2, then return fib n plus fib n minus 1. else return 1. Okay, so that's the core of the function that we've done. So, you know, one kind of test is if we go into CD research code. Yes. Oh, and it ceases to scroll. That's wonderful. I can run Python fib. Oh boy, fib underscore and. So it's just the faces are over the code, so it's kind of hard to see. Okay, so well, it doesn't crash, so that's good, right? So if we call it, it doesn't crash and burn, so that's fun. And then we said that, you know, wouldn't it be nice if it was correct? So one thing we can do is call fib, and we can print, you know, what fib0 does, for instance, and we can print what fib2 does, or fib4 does. And we said that, you know, we expect that fib0 is 1. We expect that fib2 is, remember, 1, 1, 2, so it's 2. And then after that, it's 1, 1, 2, 3, 5. Yeah, I think so. Okay, so does it give the right thing? Oh, there's a problem. Okay, so now, you know, there's a particular issue in the code. I actually made a mistake on purpose when I wrote this code, but I made another one that was not on purpose because, you know, it's not caffeinated enough. So that's great, perfect. So we see here an example of, you know, the code doesn't crash to start with, but it has a logic error, and, you know, we want to avoid that. So the first step is to fix this by just having this like very small scaffold that can try different parts of the code path and that can try different inputs. We immediately see that there's a logical error inside the code, which we might not have uncovered until much later if we had not like written these simple print statements. Okay, so this is the error. So, you know, I was just calling fib with the same thing over and over again. So that's the first error. So if I rerun it again, now I think we'll get a much more subtle error, which is we were expecting 1, 2, and 5. And we're actually getting 1, 1, and 3. So can anybody tell me what is the mistake in the code that is causing that? Or message? Vale, I see that you're staring deeply into the screen to find out what the thing is.
You see, I have 2 screens and I'm still too afraid of saying something stupid.
That's totally fine. You know, we're in a learning environment. There's no bad answers. And I even made one more mistake than I intended to in writing this code. So, you know, it's all good. I didn't initialize. So I didn't initialize n here, but this function doesn't have any, it doesn't hold its own state. So it's actually fine that I'm not initializing n, for instance. So we can go back and actually debug this code a little bit. So what's going on is here is, so if we look at this function as a whole, if the input n is equal to 0, it returns 1. If the input n is equal to 1, it also returns 1. But what if n is equal to 2? Well, it actually like go right here. Right, so it will actually go through this code path because this is supposed to be greater than equal to 2 rather than greater than 2. Yeah, I didn't include the 2. Exactly. So print, So if n is equal to 2, print uh-oh. So I can do this, for instance. Oh, you can see, oh, it says uh-oh, uh-oh, uh-oh. So that's no good, right? So from that, we can infer that we're taking a code path that we shouldn't be, because our the way that we're doing the if-else statement is incorrect. So we can fix this. And what I'm going to do next is just, this is not test-driven development. This is debugging by print statement. I'm sure you've done this. Everybody does it. I did it in the last few hours. What I'm going to show you next is a special trick that is going to transform your print statements into super powered testing things. And it's going to change your life forever. And I don't want to oversell it, but it will. It definitely will. So we're going to replace this if statement and this print statement by an assert statement, right? So the assert statement is going to say assert n is not equal to 2, because this should never happen. You should never get into this the situation with n is equal to 2. And so assert is it's a Python statement that asserts the truth of the value which is next to it. It doesn't have any parentheses, so it's a statement. You might have seen it in other people's code and might not have totally understood what it was for. But the goal is, the goal is, if the code is correct, the assert does nothing. It's a no-op. And but when your code is incorrect, it yells loudly to tell you help, you're doing things totally wrong. This is not correct. So you write your own assert statements. So these expectations and these comments that we wrote here as print statements, we can reshape those as assert statements. Right, so we're asking of the code, just make sure that when you do this stuff, you get exactly this output. And by that, I mean, when you do this stuff, make sure that the right-hand side is true. And that's it. So now we're in a situation where our assertions, none of our assertions are actually working, right? And our code is yelling at us, telling us that there's some errors. So we're going to fix the code. Greater or equal than 2. And now when we rerun it, nothing happens. That's all that test-driven development is. If you can use this this simple trick, this one-word trick, to transform a print statement into an assert statement, you'll have code which is a lot more robust. So what happens here is that all these things about what the mathematical definition of an assert statement is, of the Fibonacci sequence is, and all these statements about whether something should follow a given code path, you're codifying it in terms of this, which is an inline assert statement, which is not quite a test, but it is something that you can use to verify that the inputs are exactly what you expect them. And I would highly recommend actually that you try this instead of using a print statement, for instance, where you would normally use a print statement to just check that the values of the variables are correct. It's better to use an assert statement, because you learn to ignore the print statements if you use them a lot. And oftentimes we comment them out. Does this happen to you? You're like, oh, great, I figured out that my code is working. Now I'm going to either delete or comment out the print statements that I have. Don't do that. Just replace it with an assert statement. And then here, we've codified the 3 expectations that we have about the code. We could also codify, what we want when we give bad inputs, for instance. So we could assert that fib -1 is equal to something. Or we could codify some complex things, like this code is incredibly inefficient because it uses recursion and doesn't cache the intermediate results. So actually, if you try to run fib of 25, it'll take, or fib of 50, it'll take the age of the universe. So don't do that. But you need caching. So as you refactor in order to include caching in the code, and so that it's more efficient, you can check that you didn't, mess up your calculation and that it still works correctly. So how can you decide what to test? So if something caused a bug, test it, right? Because 70% of bugs that you'll figure out are going to be old bugs that just like zombie bugs that keep reappearing and reappearing and reappearing. If you manually checked if something yielded a reasonable result, write a test for it. And so now you might be wondering like, yeah, but the way that I check that the result is reasonable is by looking at the figures, right? And if the figures look about right, then, you know, one of my components doesn't look like it's an artifact component, then I can say the thing is good. So what I would say is it's easier to encode requirements which have to do with numerics. Anything that's output, the figures and so forth, it's always a bit harder. So if you can split out your code in a way that the numerics and the plotting is not done in one big bunch, you can test out the numeric code by itself. And if you do that, if you get into that habit of separating out these two things, what that means is that your core numeric code is going to be well tested, and it's going to be well structured with respect to whether the figure code is embedded inside of it or not. So as a consequence, you'll get better code quality. Okay, so what will this effort give you? So you'll decrease bugs because you'll uncover silent bugs, which you'll fix immediately. You'll get some peace of mind because you know when your code is actually correct because you've defined the conditions under which it can be correct. You get easy refactors, as we've discussed. You get docs because, you know, docs have a half-life of about 3 months. After 3 months, they just poof into the ether and they become irrelevant to the original code because your code has changed and the docs haven't. But the assert statements and the testing, they go on. And if you run the test regularly, then you know you'll immediately find if the tests are no good anymore, and you'll write better code. Okay, so how do I go about this? I just told you about assert. So assert is the lowest hanging fruit, and if you just use this in your code a bunch, I think you'll write much better code. So it throws an error if the assertion is false. It's great for inline tests. So the test that was inside the function, that's an example of that. So one thing that I really like to use assert for is to check whether the shape of a matrix is correct after I do a permute operation. So if you do a lot of numeric code, you work a lot with tensors, you work a lot with like PyTorch and like moving it's terrible. It's terrible. It's like really, really error prone. The correct way to do this is to use named tensors, but they're still bleeding edge and they're not in the main line and they're not fully included. The second best thing is to use assert statements to make sure you're not shooting yourself in the foot and then you don't mistake your time dimension for your X dimension or vice versa.
I'm thinking of how many times I have drink shape in my code.
Yeah, exactly. You just replace it.
Yeah.
And one thing that's very nice, actually, you might not know this, but you can directly compare a shape to a tuple. So you don't have to write, for instance, assert shape 0 is equal to 1 and assert shape 1 is equal to 8. You can assert shape is equal to parenthesis 1, 8. And let me write that down because I realized that okay, so I just wrote it. So this is a particular example where you might use this. The second step above this is to hide code behind if __ name is equal to __ main. So this is for code that's like library code. So if you have a big Py file that contains a bunch of different functions and the way that you're using this code is you're importing it, then you can hide test behind if __ name is equal to __ main. So let me show you how to do this in the code. That's it. So this code, so one reason why people might not want to have the assert statements in line is if they take a long time to run those assertions, then it'll slow down your code. It's not like a real concern for this code, but you might check more complicated things. Whereas this will, so this code, if you run the test from the command line, tests running, test pass. There you go. Oh, see, so I've run the test and the tests have passed. But if I import instead test fib and test, like nothing happens. So this code never runs. So the tests only run if you run it directly from the command line. So this is good for library codes, very lightweight way of testing things. But the disadvantage is that your tests might be very, very long. So what you'll notice is that as you use this method more and more, you'll end up having more test code than you have real code. And so your files are going to get like 700 lines long, and it'll be like kind of messy. So this is for lightweight tests. The other thing you can use is a test suite. So you can create a specialized file which contains the tests. And you can use PyTest and unit test for that. There's two different libraries. I like unit test, which is a controversial opinion, because at Google, I learned GUnit, which is a great name for a testing library. It's exactly like unit test. So that's why I use it, but nobody else uses unit test. So people like PyTest a lot. So just so you know. And then what this will look like in the unit test library is this. So first you'll import unit test, right? Then you'll have a class, which is a dummy class. And then any method inside of this class should have things like assert statements. So you can assert true, assert false, assert equal, assert greater. You can also import from numpy.testing to check if two matrices are similar within floating point error, that sort of thing. And then once you run this code, what'll happen is it'll just run one test after the other and give you a report like everything is broken, or one test is broken, or 3 tests are broken, or all the tests passed. So let me give you a run through. So we'll do a little cooking show here. I won't code this from scratch. So we'll just skip ahead, and the cake is out of the oven. Great. So I can run test fib.py, and there's no module research code because I didn't actually, oops, okay. So let me just do something here. I have to activate by3. Sorry, I just like run different environments and I have multiple machines, so sometimes I get confused.
We love that. That's the old Brainhack. That's the part we like the most. Real life coding and see how people make mistakes and deal with it. It's
yeah, absolutely. Okay. And then inside of there, I'm going to run Python test fib. Hopefully this will work. Maybe not. And I ran the tests. So the tests are, well, precisely what I wrote earlier. So, the fact that it should give 1, it should give 2, it should give 5. If you have the input 0 to 4, I have this. And I also tested my function when I implemented the real version of this function, that it's actually efficient by testing it with fib99. If I run this on the code, which I just wrote right now, it will crash and burn. It will, make my fan spin, and then you'll lose me for a few minutes. But with this catch version, it's actually there. And I can test more sophisticated thing. I have another example for a test here, but the point is that you can add many tests inside of a test case, as long as it's a subset of test case, and you call unit test.main, it'll recognize the tests, and no matter how many tests there are, tests. So maybe I want to, split this into 2 tests, for instance, test fib big self, right? So now I have 3 tests instead of 2. And so when I run this, it says ran 3 tests rather than ran 2 tests in 0.01 seconds. So I'll just recognize that it has a bunch of functions in there. Cool. So let's continue down this road. I just coded up the tests, so I'm doing good. All right, a hierarchy of tests can be run with a runner. So you can run. Am I still sharing my screen? You're still seeing everything? Yeah, because I don't see the green outline anymore. So
yeah, we see the slides now.
Okay, good. All right. So you can have static tests, like you can have a plugin in your editor that just checks whether your code parses and writes little squiggly lines under the code to make sure it's still, it's still valid Python. You can have asserts, you can have unit tests, that's the word that you'll hear a lot. For our purposes, a unit is a function. It's just jargon for a function. And then there's bigger tests, like you might check that like an end-to-end test is might be literally a human that is clicking buttons inside of your app to make sure that actually works. So, at Ubisoft or places like that, they have people whose name is like tester, and what they do is they just play video games all day and try to break them, which is not as fun as it sounds. That's actually very, very tedious. But the ones that we really care about are unit tests, and I would say regression tests also. Checking that the behavior before and after a change is the same. That's oftentimes very useful. So my advice to you would be to write a lot of tiny unit tests that run very quickly, because if it takes more than 5 seconds to run, you will go to Twitter, because it's really boring to wait for a test to finish. So you want this thing to be really snappy. So you saw my test in fib.py. I feel seen. Yeah. So the tests in test fib, they take 0.01 seconds to run. That's very important, the speed at which you iterate, because you're going to be running these things all the time. Okay, so I wanted to have a little open discussion with you folks. What do you think is the ratio of test code to real code in a real code base, something I might run at Google or inside of sklearn or whatever? You can write the numbers in the chat. It doesn't matter. It doesn't matter the numbers that you write. I will give jelly beans to virtual jelly beans to the person who is closer to the answer. Okay, 3 to 1. I feel like a second guess would be good. 3 to 2. 1 to 1. Yeah, I mean, those are all perfectly reasonable answers. It really depends on the kind of code that you're writing. But I remember I remember hearing that somebody was doing aeronautics, and they were saying that their test ratio was 100 to 1. So basically, most of the code is just there to watch the tiny piece of code that's actually run in the aviation systems that make sure the planes don't crash into one another, which is great. I mean, that's what it should do, right? You want a lot of people to look at that code. Okay, so for down-to-earth application, I think if you have coverage, basically the stuff that is actually tested is 80% of your code. I think that's a good aim to go. There's ways to really get into the thick of things, but I think it's just a guideline. Do I have to test every single thing? No, not really, but test a lot. It's good, especially the numeric stuff. So I'm going to try and code up more, like get part of the way through an example from a real paper. And write a non-trivial set of tests. So this is going to be a little bit of a long-winded thing, but I think you'll get why I'm doing this particular example in a second. So the pitch is, how can you compare how different brain areas and artificial neural networks represent the world? So I know that many of you are doing fMRI and working on projects which are similar to this. So I kind of tailored this to this audience, but also it's representation theory is trending right now on Twitter. So I'm like lit. So the way to do this in deep neural nets and also with fMRI, for instance, is to choose a standard battery of tests. Yeah, what are representations? Measure responses across these different systems, and then you compare the responses between the systems. Now, oftentimes we're comparing things which have different dimensionality. If you're trying to compare two vectors, that's pretty easy. You can use a correlation coefficient or something. But if you're trying to compare two matrices that might have different columns, then you have to do different things. So you could use forward encoding models to like ridge regression, or maybe canonical correlation analysis, or if you're in the Krieger-Skorte gang, you might like representation and similarity analysis. But the one I'm going to talk about today is CK, which is centered kernel alignment. And so what they propose is this new method to compare representations. It's basically the square of the Pearson correlation coefficient, but adjusted so it can be run with different numbers of columns. That's one way to think about it. So if you know about the Pearson correlation coefficient, this will feel familiar. But what's important is this little piece at the bottom, which I wrote, which is that CK is not actually implemented in SciPy or sklearn. And even on GitHub, there's very few hits, although Elizabeth just did point me to a good implementation. But it's actually like pretty hard to find. So you could easily like convince yourself like, oh, it's a great idea to actually implement this myself. And then you shoot yourself in the foot. So it's real research code. So let's think about like how we might want to implement this and test it in a way that we can be assured that at the end, when we present our results, they're good. So I think it's so the first thing is to really try to reduce the problem of this big chunk of code that we're going to do into things that are testable. So what I actually did is I just looked at the paper to see, they have some theorems about this particular method. They have, discussions about like how it works in different circumstances. And I extracted a couple of invariants or expectations about it. But the one that I'm going to focus on the most is this particular one, which is the first one, which is that if we're doing it correctly, it should end up that CK is actually the square of the correlation coefficient if the two things that we're comparing are one-dimensional. So that's pretty easy to test. That's a good invariant to check. And so now let's decide about how we might do some live coding with respect to that. So I'm going to show you some code, which, as you can see, is written ck_notgreat.py. So it's not great, but it's a start. So what this code does is it actually runs an analysis end-to-end of CK. So what it does is it loads 5 different representations from like some simulated battery of stimuli in memory, and then it compares them pairwise to get you like one of those nice little matrices of comparison that I showed in the slides. So just to give you a little bit of, and I tried to make it so that it would be like the right size of code so that it wouldn't be trivial, but at the same time, that would be like complex enough. So please tell me later. You can also like tell me anonymously if you think I hit the mark. So what we do here is we load this data matrix, and then we run the CKA analysis pairwise. This is the code that is actually the definition of CKA. I picked this code, I picked this from the paper itself, just like very naively, like I'm just gonna implement it in the most straightforward way that I can think of. And this is linear CKA, by the way, if any of you are curious. Then I take the transpose of the matrix because I don't want to calculate things twice. And then I plot it and I save the figure, and it generates a plot. So I can just run this code now. Hopefully it'll work because it won't tell me like you didn't install this or that. Okay, so it runs. So it doesn't crash and burn. So the code is correct. Sorry, no, the code is not broken. Let's call it this way. But how do we know that this computation here is correct? Right? Like when I report this result in the paper, like I mean, okay, there's a square here. There's the square root of this thing. I'm using it on some example data that I have. Like how can I make sure that this is correct? So I'm gonna take the time to look in the messages to see if anybody has like some ideas of how we might test this. Or maybe I can say like, what would be the first step in order to test this code?
To me, the only thing I ever did that was similar to this was once that I wanted a partial correlation in Python and I couldn't find it, but I knew the function in MATLAB. So the way I got confident that what I was computing in my Python script was correct was by comparing the two output, right? Like I would keep passing the same input to the function in MATLAB that was MATLAB function, so ground truth. And then I would compare my Python one and check that the result was correct.
Yeah, and that's a great observation. I actually have on my blog, I have an article on translating MATLAB code into Python that uses test-driven development, like you're saying. And that's definitely a way to do it. Just like test it on a bunch of inputs and make sure that the outputs are the same. So I think that what's going to make it hard for us to really make progress with this code is that everything is kind of like bunched up together, in a rather rigid way. So we have the inputs here. This is the numerics code. And then we have the plotting. So, but like I said, we think that this we can't really mess up, and this is, well, we're going to look at it. So, we can't really mess this up later, but this is the part that we really care about. So if we want to test it, the first thing that we might want to do is to refactor things. Refactor so that the numerics is isolated from the figure code and the input code. So that's going to make things easier. And then we can do the process that Vali was talking about, which is to verify for different inputs that it gives the kinds of outputs that we're expecting. So maybe the first step is just to take this code, which is right here. Then we take this. We define a function, CKA1. Exactly. And we so a simple refactor in which we isolated parts of the code that was doing numeric stuff, and rewrote it in a way that it was isolated from the rest of the input-output loop. Okay, so the value is this. It's very hard to name things and in computer science in general. So please don't remove points from me for that. Cool. So in theory, we haven't done anything because this is the same code as before, and it does exactly the same thing. In practice, we have actually improved the code quality in doing so, because now the numeric code is actually isolated from the other stuff that we don't like really care to test. So then the next step, going down this whole this stuff here, would be to isolate the rest of the code as well. You know, put it in its own little function, and then we might want to write this, and then it runs main. So now we have a this is a script, right? So it has like this numeric part, which is this top part, the CKA1, and it has this main function that, you know, that actually runs the script. So unfortunately, if we want to implement this strategy which I was talking about earlier, which is to hide code under if underscore name is equal underscore main, it's not going to work so well. In the interest of just, you know, showing you the ropes of testing, I'm still going to do it this way. Like, don't hold me to it, but I'm just going to comment things out for a little bit. Sometimes it's good also to remind ourselves of not good ways of doing things, so we don't repeat these errors. So I am going to just run an assert for now, and I'm going to try and assert something about CKA1. So I'm going to assert that CKA1 on some input XY is equal to some value. Okay, we're making progress. We have an assertion, right? So we had this this idea that the invariant that we were looking for is that the CK of this one-dimensional thing should happen to be the square of the correlation coefficient. So actually, let's write this as this. CK1 is equal to val square. Okay, so val is going to be the correlation coefficient of x and y. Run 0, 1. Cool. And then we just have to pick our x and y. So we can even run it with random stuff if we want to. Let's do this. Let's do that. Why not? I mean, it should work for any two inputs, right? That's the gist of the assumption here. So does this work? I actually don't know. So it says assertion error. This isn't quite correct. So it just ran this, and it found that it wasn't quite right, in fact. So now we can go back to our usual like debugging by printing, because we're in a learning kind of environment, so it's all good, and figure out what's wrong with this. All right, so it's actually giving us a NAND for this particular set of inputs. So let's see, it printed the value of this, and then, that's interesting. Is Elizabeth awake? Because I'm sure you can find my bug.
No, I'm here.
Oh, you are.
Let's see.
What's wrong with this exactly?
Wait. I was. Can you? Where are you looking? What are you trying to find?
So I'm trying to find out why my value print val is nan.
Okay. And your x and y.
So that's the correlation coefficient.
Mm-hmm.
And actually, I can just print this. Nan. Oh, I get it. Oh, Patrick, come on. You can do better than this. I'm just kidding. Okay, so now we're in a better spot. So we can see, I can actually print the square of this value. It says the assertion, yeah, real life. So it says here that, the assertion is false, but when we look at these values, they look pretty close to one another, right? They just happen to differ in the last few digits. And if you know about numerics in computer science, that floating point values are, there's always some error which is associated with them. So sometimes if you run the same calculation through two different means, you'll get two slightly different results. What's important is that they match each other in within a certain bound. So there are ways to help you deal with that. So you can look at np.testing.assert all close if you're going to do this for a lot of matrices. But in our case, we're just going to check that this value here is close enough to this value by checking that the absolute difference is smaller in some amount. So it's going to be an absolute test. So let's looky here. And it's smaller than, I don't know, let's say 1e⁻⁹. So that's something that we have to deal with when we deal with floats is, as you know, they can change a little bit and flake on us. And that's it. So in this case, when we print, it prints similar values and it doesn't throw an error. And so if we had done something very silly with our code, like let's say that I had forgotten to center my variables before I calculate this, if I rerun this, it would tell me like, no, actually like this, there's an error. There's an assertion error. This is not correct. So if, let's say that I rewrite the code in some way so that it's more efficient or it runs under a wider range of cases, then I can be confident that my code is still going to remain correct because I have the scaffold. So the next step after this is to take this code and then, whereas here we wrote it in __name is equal to main, we can write it as a separate test. So this is the whole test suite that I wrote for this code. And let me show you the one that tests the correlation. This is the test right there. In this case, it uses assert almost equal, which did the thing with the absolute value, which is smaller in some amount. It's exactly the same principle here. But I also test a bunch of other things. So if you notice, my test scenarios, there's 100 lines of code to test, 5 lines of numeric code. But after I run this, I can be assured that it actually does work. So something interesting, so I was actually using CK for a project, and I actually noticed that there's another implementation, and another implementation is actually more efficient under some circumstances. And so I had to write like kind of complex code so that under some circumstances use this branch of code, and under this other set of circumstances use this other set of code. And it was really easy to figure out if it was working or not because I had all this stuff. It was a contract basically that I'd given to myself to make sure to check off these boxes. And at the end, I could report these values and be 100% confident that they were what I knew they were. So that's, I think that's the end of the presentation, mostly. Actually, the one thing I would say is, to really integrate this information, your 5-minute assignment is really find out some commented out print statement in your code right now. Just do it like right after this and replace it with an assert. And if you do that, I guarantee your code will become just a tiny bit better, and it will set up a mechanism to improve it further in the future. So we're all out of time, but I can still take questions if people have some.
I see lots of clapping, but you guys remember you can type your questions, turn on your mic, whatever works better. I definitely join the applause. I promise, I will remove at least 4 3 statements or 4 scripts this afternoon. I know I can.
Sam?
I'm also going to stop the recording because I know that